I wonder if I could play this. You think if I press that, it'll play?
Sometimes.
Yeah, normally you can just click on the link and then I'll just like open up and do it.
Sometimes it doesn't.
Sometimes you have to hit like control and then press on it. That works too.
Control.
Normally that's more of a Word or email thing.
Yeah, sometimes you get a hand. Well, let me just explain that. The homework I'll give you, this video is embedded in Moodle under Resources. And the last problem that I have so far on the homework directs you to that video, a little short 8-minute video, which will pretty much summarize the three major things we're going to deal with today. We're going to deal with really understanding this, this, and this, or these are all velocities or speeds of molecules. The root mean squared velocity, the most probable velocity, and the average or mean, the mean velocity. And there are equations that define each one of these. So that's how far I hope to get today and finish chapter 19 on Monday, not Monday, Wednesday, next Wednesday. All right, so just to put 19 and 20 together, so last two chapters. 19, we're not going to deal with any chemical reaction whatsoever. We're going to be talking about the behavior of a gas, and we'll be talking about it basically as an ideal gas. And we're going to be talking about atoms or molecules. I'll probably always be using the word molecule, a gas molecule bouncing around inside of a container. So we're going to look at it from a classical, so this is physics. This is basically physics. How do things move? Classically, it's not going to be dealing with quantum mechanics at all. Just what is going on inside of a container filled with a gas? How is that gas moving? Where is it going? What is its velocity? How is that related to other things? So let me just finish. How does this relate to chapter 20? Well, chapter 20, we're going to get into kinetics. We're going to get into the rate of chemical reactions. Well, what is one thing that has to happen before any two entities can react? Two molecules.
They hit each other.
They have to hit each other. They have to collide. Does that necessarily mean, if two things collide, does that mean they do react? No. They can collide all the time and not react, fortunately. When you're putting gasoline in your car or in a lawnmower or whatever, gas molecules, gasoline molecules, and oxygen molecules are colliding all the time. Right there, right in front of you. But they're below their auto-ignition temperature, and there is no effectual reaction. All right, so collision is a necessary prerequisite for a chemical reaction, but it isn't the only prerequisite. There's other things that have to be in there. So what we're going to be looking at is really we're going to look at gases, but the author says, you could kind of think of this down, you could go back down and look into a liquid and just imagine that the liquid molecules are moving around, not by as simple mathematics that we can look at a gas particle, but they are moving around and they are bumping into each other, and that's what has to happen for them to react with each other as well. So that's kind of the relationship. So we're not going to belabor chapter 19, but we want to just kind of understand it. Okay? So, and what you'll find in the homework, well, I'll tell you that. That's good news later. All right. Here's the beginning of the chapter, and I left this byline off too much, but just know that that deserves to be on most every other handout I've given you, that it's really from this. What we find in this chapter is that physical behavior gases can be understood if some simple assumptions are made. We're going to treat them as hard pieces of matter, solid spheres, basically. They can predict some of the properties by applying classical, not quantum mechanics, but just classical Newtonian kind of concepts of how things move around.
What are quantum mechanics?
Well, quantum mechanics are some of the statistical thermodynamics, the looking at the electron as a particle and a wave.
Okay.
It gets into quantum mechanics. So we're not looking at the electron here. We're looking at the atom or molecule, which has the electrons. And basically, if you think about it, the atom is transporting. One atom is transporting the electrons, and another atom is transporting the electrons to a point where they do collide, and now there is some interaction of the electrons. The electrons aren't flying around from atom to atom. They're around the atom, but when those atoms get in proximity, then the electrons can transfer. You get a chemical reaction. So we're not looking at electrons. We're looking at the molecule or the atom. But yeah, here are some of the standard assumptions that go into the kinetic molecular theory of gases. They're composed of tiny particles of mass, so they do have a mass. They're in constant motion, and we're going to do an example here, and kind of amaze me how fast these things are moving, even at temperatures below, below, at fairly, not real low temperatures, but below the freezing point of water. These little babies are moving. They're in constant motion. They're moving in a straight line until they hit something, whether it be another molecule or the wall of the container. They're moving in a straight line. They hit something and they glance off of it and get a new direction. They cannot collide with each other in the walls of the container. But what we're going to talk about today is these collisions don't result in a chemical reaction, and they conserve energy. They're perfectly elastic collisions. The speed of them won't be exactly the same. It depends. You know how it works with bumper cars. If you want to knock your cousin further on the bumper car than you get up to speed, and bam, and they go flying off, and you just stay there. But energy is conserved. Okay? So if you looked at your momentum and your cousin's momentum and added those two together, that basically, there's a little friction even in bumper cars, but basically, probably a better example is two hockey pucks or a hockey puck bouncing off the walls. Very little friction. Okay, so those are some of the assumptions. And I will go, these are some of the key equations. We're going to focus on this one for about 10 minutes. But here's these three speeds. And you can see there's a chemical relationship, and they're derived in this chapter. You can see we jump from equation 13 up to equation 35 and 36. Now there's about 6 pages of the book in there that we will, I don't say ignore, but we won't. I'd like you to skim them anyway, all right? Just skim them, but there's a lot of equations, a lot of derivation to go from here to here. I think we get to here from there pretty simply, or relatively simply, and then it's a little bit more complicated to get from here to these last two. But so you got a root mean squared velocity of a particle, or a number of particles, most probable speed, and a mean velocity, v with a bar above it. Okay, let's take a look at this one. How do we get to an equation like this? let me just go down a few more. There's only about 20 slides here. I'll probably add a few more. See, where's this box of mine? Not of mine, but of the authors. Huh. I don't see it. All right, let's look at this equation. We'll get down to it. It'll show up, hopefully. We want to derive this, and we got pressure, volume, Avogadro's number, basically mass of an individual gas particle, and then this V squared average. I'm not sure that directly correlates to this velocity right here. You'll see here in a minute how we get to there. Okay, some equations that you've probably seen before. So here we're talking about kinetic energy is equal to 1/2 the mass of a particle. I mean, if we were talking about, a basketball or any kind of a ball, the mass of it times it's the square of its velocity. 1/2 the mass times the square of the velocity is a relationship for the kinetic energy of that object. Force is equal to mass times acceleration. Okay, what is acceleration? It has a time factor into it. The change in velocity with respect to time. So that gets you from there to here. All right, so at one point here, we're just talking about a single atom or a single molecule. So we just got the mass of a single molecule. We're looking at its motion, its velocity, its acceleration, etc. So then if we want to start talking about the total force of a container with Avogadro's number of atoms in it, we can get to a relationship like this. The total average force, each one of them has a different force. They're not all there's a distribution of velocities among these atoms. They're not all going at the same speed. Even if they're in a container at the same temperature, there's a Boltzmann distribution of velocities among these. Some are moving slow, some are moving really fast. There's a swath of, the average velocity in the center. All right, so when we just look here, we're looking at the force of a single atom. Its mass times its acceleration. So the average then is the total number of them. 1 over time, we're integrating this and getting rid of these derivatives, coming to an equation like this. 1 over time times the mass of the individual atoms times the change in the average velocity of those atoms. All right, now here's the box. So they're looking here now at a certain arena, where a certain container, where this atom, this individual atom is bouncing around. It's moving in straight lines until it hits something, bounces off of it like a ping pong ball or a hockey puck would bounce off the walls of the sheet of ice. Glances off at an angle. Here, these dimensions, the width of this box, the height of the box, the depth of the box, A, B, and C. Now don't get confused. A is going to start showing up in here not as acceleration, but as the dimension of this box. And what they're looking at here is how much time does it take for that particle to make it, if it hits the wall over here, how much time would it take it to get back to the other side? And so you got this, so the V average sub x right there means we're looking at the movement of this particle in the x direction. All right, we're kind of limiting it. We're simplifying it, saying, let's just look at one direction because velocity has 3 vectors to it. All right, so let's just look at the x direction, and that velocity is going to be twice this distance, 2a, to go from here over to here and back again, divided by the time that it took to do that. So then rearranging that, you have time equals 2a over the average velocity in the x direction. So going back to that original equation, the F average total in the x direction is the total number of them, the mass of each one of them, times the square of the velocity, the average velocity in the x direction, divided by a. Let me see. Is there any way I can look at both of those slides at the same time? Okay, notice we've squared this now. Why did we square that? Look at this. Look at that for a second. Here's the previous. We got time here. And if we take that relationship for time and plug it in right here, so time is 1 over 2a delta v average times m times delta v average times n. This is our total average force, okay? All I'm doing is going the next slide, taking the expression for time and plugging it in right there. And so you invert that and you get delta V average squared divided by 2a. Wait a minute, how do we get rid of our 2? Okay guys, help me here. How are we getting rid of the 2?
1/2. It's got to be from 1/2 mv squared. Force, or kinetic energy, 1/2 mv squared. That's the only thing I can think of. Is how you multiply by 1/2, you get rid of the 2. But other than that, I don't see where we would.
Well, that's a little bit, because we haven't invoked that yet. We haven't pulled in the kinetic energy into this whole thing.
Well, normally you don't mix forces and energy. If you're using kinetic energy, that's like a different equation. Like, anytime you're using accelerations, you're normally not dealing with kinetic energy. It's all based on force.
Yeah.
And
Well,
that looks like what it is right here.
Take a look at where are we? Right there. That's something I'm just noticing right now, that factor of 2. Oh, wait a minute. there, in the previous equation, there is a 2 in there. Now, why is there 2 in there? Okay. The precursor equation really has a factor of 2 right here. And so the 2's are crossing out. All right, you look at it. You look at it. But
Why would there be a 2 in that?
well, because
Where did the A go?
the A is still there. The A is
See.
still there. But the 2 has to do with the fact that the delta V average is going to be 2 times the V average in the x direction. So that a factor of 2 comes in there. Let's not belabor it right now, but there is a factor of 2 that gets into here. So then when we do this, it simplifies to this equation right here. Okay? Keep this box in mind because I need to go to the next slide. We're going to lose this. What you'll see, I think, on the next slide is that A times B times C is what? What's A times B times C? The volume. Okay? So we're going to get a volume term coming on into these equations right now. And we're going to get a pressure term in there. What is pressure? Pressure is force per unit volume. Or per unit area, excuse me. Force is, or pressure is force per unit area. So we got pressure, it's force per unit area. So there's our force from the previous equation. There, we're going to divide that by B times C, that's the area. So we're going to divide this side of the equation by B times C. And what do we got? Lo and behold, A times B times C is volume.
Where did that A come from? I know it's A times B times C equal volume, but I see that average force equals NM velocity squared, right? So I see where that term comes from. I just don't know how the A gets in there when you have previously that B times C, and then you just throw in the A times C.
Oh.
Okay, this A, Liz, is not acceleration.
Oh, there it is. Okay.
This A is looking at, we got this box here of certain dimensions, A, B, C, but we're only looking at the x direction vector on this particle for right now. We're going to get away from that in just a second. But for right now, we're looking at just the x direction. Mm-hmm. Saying how long does it take it to go from one wall to the other wall?
Yep.
That's where that A comes in there. Whoa. All right. So I knew I was low on charge, but I forgot. I need to plug this in right. Okay, we want to get to a point where we can at least do a few calculations. All right, so A times B times C is volume, so we're going to replace that with volume. Notice we just arbitrarily said, let's just look at the x direction. Well, there's nothing magical about the y or the z direction. It's not like these 6.02 times 10 to the 23rd molecules like the x direction more than the y or the z. They're behaving ideally. They're just a statistical gamish of what they're doing. So those are all equal in the x, the average. So for one particular particle, yes, we could say the x is different than the y or the z, but statistically speaking, the average of the velocities in x the y or the z direction are going to be identical. So the overall average velocity, the square of the average velocity, is going to be the average of all of them going in the x direction, the y vector, the z vectors, add those up. So this overall average, irrespective of direction, is 3 times the square of the average in the x direction, which what we were limiting ourselves to at this up to this point. So what does that mean? This means that what does this mean? That v squared average in the x direction equals the overall v squared average divided by 3, right? So we're going to plug this in place of that, and we're going to plug this in place of that, and we're going to get down to this equation. Pressure in this container is Avogadro's number times the mass of the atoms or molecules times the square of the average velocity divided by 3 times the volume. And notice all of a sudden here we've got 2 of our ideal gas law variables pulled into this relationship. All right, so let's do this problem. For 1 mole of helium gas, a volume of 25 liters of gas exerts a pressure of 0.8770 bars. What is the average velocity of the helium atoms in the system? And it's 0.8770 bars. We want to get this, we want to get pressure in newtons per meter squared. This is SI units. Newtons per meter squared. And one bar is 10. Oh, what happened? Is 10 to the 5th. Oh, this thing has a mind of its own. Why is it doing this? It's 10. Oh, okay, 1 bar equals 10 to the 5th pascals. And and 1 Pascal equals 1 Newton per meter squared.
So we don't need to worry about the volume in this case?
Yeah, you do.
Or we do, okay. We need the volume.
Yeah, you need the volume. And what they want to know, the average velocity. And we got two ends in here. One end is Newton, and one end is oh, wait a minute.
Oh, so we can express pressure as Newton meters squared.
Yeah.
That's how you solve this problem.
Yeah. Well, yeah, n times m, so Avogadro's number times the mass of one particle is going to be its molar mass, right? The Avogadro's number times the mass of the individual helium atom is going to be the molar mass of helium. And you should put that in terms of kilograms per mole to stick with SI units. So the pressure is 87,700 newtons per meter squared.
So what's the mass of?
That's 4.003, is that right? 4.003 grams, or 0.04003 kilograms per mole.
Wait, yeah. Does that make sense? That it's, I mean, these are grams per mole, right? Why are we multiplying it by the number of molecules? Oh,
Well, the M would have been 4.003 atomic mass units.
okay, which is grams.
Which also the same as grams per mole.
Right. So if you have a mole of them, then you have 0.04003, or you have 4.003 grams of them, or 0.04003 kilograms. That should be 0.00, right?
Yeah.
Yeah, 0.00.
Why are we?
So you don't need the per mole in there. Why don't you need the point mole in there? We just got Avogadro's number. That's the number of particles. You're saying we've got 1 mole of helium. How many helium atoms is that? That's 6.02 times 10 to the 23rd helium atoms. So we're just replacing mole with Avogadro's number.
Okay.
So we don't need to say it's 6.022 times 10 to the 23rd per mole. We've got 1 mole of atoms, helium atoms. So what kind of pressure would they exert? One of them would just be its mass. Avogadro's number of them is going to be that mass of particles. So 1 liter is 10 to the minus third cubic meters, right? A liter is a deciliter on a side, a tenth of a meter on a side. So that's 10 to the minus third.
Wait, so we actually do not need to write in 6.02 times 10 to the 23rd.
No.
And calculate with it at all. It's just there.
Yeah, if you did, you'd have to multiply it by the mass of a helium atom.
Divided by the molar mass divided by 6.02.
Yeah, so it just cancels.
There, yeah. It's like, I see.
Yep.
Yeah, so Dominic, I think this is right. I think that's the mass of an atomic mass unit.
Oh, I see. Okay.
See, so this is what's on the periodic table.
Yeah.
Remember, what's on the periodic table is unitless. It can be taken as the mass in atomic mass units of a single atom, or the mass in grams of a mole of those atoms. So what's on the periodic table doesn't have a unit there. It can have either unit, atomic mass unit for 1 atom, grams for 1 mole of those atoms. So that's what we're getting to here. We're just getting down to 0.004003 kilograms of helium atoms. Okay, so what do we get? So now we got V squared average is a certain number, and so V average is going to be the square root of all that over there. And does somebody get that down to an answer? Someone get a number? Taja, yeah, we count on you, Taja, back there. See, she's back there punching in things in her calculator. 1281.9. 0.9, and the units are meters per second. Meters per second. Okay, let's say that's 1282 meters per second. So we're going to multiply that by 60 seconds per minute and 60 minutes per hour, and we're going to divide it by 1 kilometer per 1,000 meters. And what do you get out of that?
3,600 kilometers per hour.
Yeah, greater than 3,600 kilometers per hour these helium atoms are moving. Now you might think, well, I wonder how hot these are. Well, in a later example, the author's going to have us go back and say, okay, what temperature? He's going to use another equation to say, okay, what's the temperature of these helium atoms? And you find out it's something like 264 degrees, 264 Kelvin. So it's less than the freezing point of water. Helium atoms are moving at 3,600 kilometers an hour. So those little helium balloons, you think, what keeps that balloon out there like that? Well, those little babies are smashing into the side of that balloon really fast.
So why doesn't it produce a lot of heat? Is the mass so small?
Well, it's the collisions aren't producing heat. Heat's producing their velocity.
Oh, okay.
Right? Remember? Their velocity is proportional to their kinetic energy. Their kinetic energy is directly proportional to their absolute temperature. And remember, kinetic energy is 1/2 the mass times the square of the velocity. So the temperature, kinetic energy is directly related to temperature. It's directly related to the velocity. So they don't produce heat. It's the heat that produces their velocity. You cool them down, they move slower. Heat them up, they move faster.
They don't produce heat because it's the elastic reaction. So
Oh, yeah.
there's no energy
There's no
loss.
friction. So what temperature are we assuming these are at? Or are all helium atoms at this temperature? Or like what? You see what I'm saying?
All of the helium atoms are at this temperature, and it drives this to this average
Okay.
velocity. All right, so I mean, that's just astounding that they're moving that fast. Yeah, and here's the solution to that one. All right, let's just take a peek at this for a second. So here's kinetic energy. So now they're just coming off of what we just said. So the average kinetic energy is 1/2 the mass of these particles times the average velocity, square of the average velocity. All right, and if we substitute from there into our previous equation, we get an equation like that. Now, here's where we're starting to look real similar to our ideal gas law. We've got an expression for the pressure times the volume. So take the pressure times its volume, multiply both sides by volume, and get this: 2/3 the number of the particles times the average kinetic energy. So we know that PV equals nRT, so all of a sudden now we could substitute this for PV, and we've got a relationship here now. The number of particles times the average energy is 3/2 times nRT. The average molar energy here, 3/2 RT. If we just talk about 1 mole, N drops out. Number of moles here, and we say, well, let's just look at 1 mole. So N drops out, we get to that equation. And you eventually get down here, it gives you a relationship between the ideal gas law and the Boltzmann constant. And the author here is probably, at different points in the book, has said these are probably the two most important constants that you run across in chemistry and physics, is the ideal gas law constant and the Boltzmann constant. And they're related to each other by the Avogadro's number. Okay, now you eventually get to here. If you take the square root, you take the square root of that v squared average. So you're taking the square root of the square of an average velocity, so it's called the root mean squared velocity or speed. Root mean squared speed, and you get this relationship here. Okay, I'll tell you what, I'll have you take a look at this, and there's this example. What is the temperature of the helium sample in the example we just did? If that average velocity was considered to be the root mean squared velocity. So here we got a temperature term in here. So if you take that number we got, which was 1282 meters per second, and solve for this for helium, you know, solve for T. And that's what we'll pick up on Wednesday. Now Wednesday, I don't know if I'll have any more problems to add here as we get into the rest of chapter 19. But I'll give you a strong hint. 1, 2, 3, 4, and 5 are mimicking the examples that are in the textbook with just either changing the temperature or changing from helium to argon or neon or something like that. So it's just patterned right after the problems in there. And then number 6 is the one where you need to listen to this 8-minute video and answer a couple questions about it.
And this will be due next Friday?
Yeah, I think next Friday is good.